Welcome. This is part 5 of um, structural mechanic 3, where we are going to do another set of worked examples. Consider the photo frame illustrated in figure Q3. Figure Q3 is shown here. Is a photo frame 3 meters by 4 meters. We have 2-point load at this point and this. Okay, the frame is subjected to 2-point load P1 and P2 acting at the middle point of the top and left member respectively, as shown. Okay, the two vertical members have plastic moment capacity MP, while the horizontal member has a plastic moment capacity SC times MP. Use the virtual work method to answer the following question. So question A, state the total number of possible collapse mechanisms, including independent and combined, and also state how many mechanisms that can be skipped without affecting the calculation of the collapse. So the total number of independent mechanisms is given by N is equals to H minus I, which we determine in the notes as shown. So you can use two methods, virtual work and to solve the photo frame problem. So the number of independent mechanism for a generic frame, the number n of independent mechanism is given by n is equals to n minus r, and n is equals to total number of possible plastic hinges. R is equals to number of redundancy. So we have how many plastic hinges? We have in this example we have 1, 2, which are marked with a yellow dot. 1, 2, 3, 4, 5. They are 5. Okay, they are marked with yellow circles. So 1, 2, 3, 4, 5. Now this one is here because of this point load. Okay, number of possible plastic hinges. So this point load is causing this one to have an extra a plastic hinge here. Now this one is this corner we have one plastic hinge, this corner and this corner and this corner. Now independent mechanism, it can be beam and sway. So this beam can fail due to this point load, and they also sway. So let's go back to the answer. So here we have total number of independent mechanism. Now we will be having one here, that is 1. There's an extra one here, 2. At this corner, 3. At this corner, 4. At this point load is the 4th, and this corner 5, and then this support 6. So we have 6 possible plastic hinges. Number of redundancy will be equals to I is equals to R minus 3N. Okay, which is equals to number of redundant. So let's go back to the notes. So number of redundant. The number of redundants in this, we are having 3 redundant. Okay. we're having 3, and for here we're having also 3 redundant that given by this formula, that is R minus 3n. Okay, so is equals to I is equals to 3. Now n is equals to 6 minus 3, which is equals to 3. So there are 3 x times independent mechanism. That is, we have the top beam, the side beam, and the sway. But from this example, we have 2 independent mechanisms. That only the top beam and the sway. But now because this point load is at this midpoint, now we're having an extra independent mechanism, this side beam. So we're having now the side beam, the top beam, and now sway. Now there are 3. So there will be 4 combined mechanism in total. That is top beam plus sway, side beam plus sway, top beam plus side beam, and top beam plus side beam plus sway. So the mechanism 6 and 7 can both be skipped without affecting the calculation of the collapse load. Now this is because no hinge rotation will be cancelled when combining mechanism 1 and 2 together, or when combining mechanism 1, 2, and 3 together. Without any cancellation of the hinge relationship, the collapse load for this combined mechanism will lie between the maximum and the minimum collapse load of the contributing individual mechanism. As a result, the resulting collapse load cannot be smaller than the minimum of the collapse load of the individual mechanism combined. So the calculation of the collapse load for mechanism 6 and 7 can be skipped. Question number B. Identify all possible collapse mechanisms that can be skipped. So we have answered this question. Now plot a graph with P1 against P2 showing the region of safe load, combination, and the failure envelope. Further find how many load combination will with 2 possible collapse mechanisms. So one is top mechanism. So this one is question B, which can be determined with this algebraic question. We can be after simplifying, you will get the answer of P1 is equals to 2.8067 MP. There is a side mechanism which can be determined by this algebraic question, which can be simplified into P2 is equals to 2 MP. Now, the sway mechanism, which can be determined with this algebraic question, that is P2 into delta over 2 is equals to MP theta plus MP theta plus MP theta plus MP theta, which can be simplified into P2 is equals to 2 MP. Now there is top beam plus sway, which can be determined by this algebraic question, which can be further solved and simplified into 1 plus 0.5 P1 plus 2 P2 is equal to 6.21 MP. Now that is question B. Now question C. Plot a graph with P1 against P2 showing the region of safe load combination and the failure envelope. Further find how many load combinations with 2 possible collapse mechanisms. So this is there are 5 possibles. As you can see, this is still in question B, the possible collapse mechanism. Now question C. Calculation for top beam plus sway mechanism needed to plot the graph of P1 against P2. Now collapse load combination 1.5 P1 plus 2. P2 is equals to 6.21 MP. Now when P1 is equals to 0, 2P2 is equals to 6.21 MP and P2 is equals to 3.105 MP. When you simplify, divide by 2 both sides. Now, when P2 is equals to 0, then 1.5 P1 is equals to 6.21 MP, which is equals to P1 is equals to 4.14 MP. Now, the graph can be can be as shown. The graph demonstrates that there are two load combinations that have two possible collapse mechanisms. These two critical load combinations are denoted on the graph as C1 and C2 respectively. Now further find how many load combinations with two possible collapse. So we are in question D now. Determine this is the answer for question C, part 2. Now further find how many load combinations with two possible collapse mechanisms. Now you substitute the collapse load combination for top beam plus sway mechanism in that algebraic equation. Now you get that P2 over P1 is equal to 0.7009. Now when P1 is equal to 2.8067 MP, substituting into the top beam plus sway mechanism, get that P2 over P1 is equal to 0.3563. Now if you plot, the graph will be as shown. You can see the side beam plus sway, the top beam plus sway, and the top beam mechanism. And the P2 over P1 is less than 0.00970009. Now this one is 0.3563 is less or equals to P2 over P1, which is less or equals to 0.7009. Now this one is P2 over P1 is less or equals to 0.3563 in this lower region, this middle region, and the top region respectively. Now we're in question D. Determine which mechanism causes plastic collapse when P1 is equals to, now the number you determine for yourself times P2, and further check whether the yield condition is satisfied or not by sketching the corresponding bending moment diagram with the key bending moment marked. Now when P is equals to 1.105 P2, then P2 over P1 is equals to 0.9005. Plastic collapse will be caused by side beam plus sway mechanism in this scenario because 0.905 is greater than 0.7009. Labeling point of the frame as AF according to the following diagram. For the side beam plus sway mechanism to develop, 4 plastic hinges are required at the frame position A, B, E, and F. Initial sketch of bending moment diagram based on visual inspection is as follows. No need to check the current unknown value of bending moment at frame position C and D. For yield condition to be satisfied, the following condition need to be met. That is, BM at C should be less than MP. That is, BM at D should be less than 1.105 MP. Taking moments at B, using that algebraic equation, you get that HA is equal to MP. Taking moment at E, using this algebraic equation, you get that VA is equals to 0.4954 MP. Taking moment at C, using this algebraic equation, you get that BM at C is equals to 0, which is less than MP. Now, this indicates that yield condition is satisfied. Taking moment at D, using this algebraic equation, you get that BMD is equals to 0.7431 MP, which is less than 1.105 MP. Therefore, yield condition satisfied. A sketch of actual bending moment diagram is as follows. Inspection of the bending moment diagram indicates that the yield condition has been satisfied. This confirms that the side beam plus sway mechanism is the actual plastic collapse mechanism for the structure. Question 4. Consider a frame shown in figure Q4. The frame is subjected to two-point load. The plastic moment capacity of the members of the frame are MP, 2MP, and 3MP respectively as shown in the diagram. MP, 2MP, and 3MP. That is figure Q4. Choose a set of internal or external reaction force to draw the bending moment diagram of the frame. Express the bending moment at some point at some key position in the term of these unknown reactions. Now, A. Labeling position on the frame as AE in the clockwise fashion according to the following figure. Degree of interdeterminacy of the provided structure I is equals to R minus 3N. That is 4 minus 3, which is equals to 1. The provided structure is statically indeterminate in the first degree. Need to split the structure up. Replacing all the roller support at E with vertical reaction force R, therefore making the structure statically determinate because initially the structure is statically indeterminate to first degree. Now using this as algebraic equation that summation of MP should be equals to 0, you get that Bm at B is equals to 4R and Bm at B is equals to 6R. That is, solving this algebraic equation, the corresponding bending moment diagram is as follows. Equivalent sketch frame bending moment diagram is as follows. BMD. Now, considering the structure with point load applied, solving this algebraic equation, we get that Bm at B is equals to negative 2.21p and Bm at A is equals to negative 8.42p. The corresponding bending moment diagram is as follows. Equivalent sketch frame bending moment diagram is as follows. Moment combined diagram BMD1 and BMD2 with bending moment at key position expressed in terms of parameter with unknown values is as follows. So I hope you can see. Now this one is the negative 8.42 and negative 2.21. Now the combination of BMD1 plus BMD2 is now as follows. Question 2. Assume the location of some plastic is determine the true plastic collapse load P of the structure. Show that the yield condition is satisfied. Now there are two unknown variables P and R. Two plastic hinges are required, which will then provide two equations from which P and R can be found. Check the solution with the plastic hinge at A. Now you get that R is equals to 1.4033P minus 0.166 MP. Now at B you get P is equals to 0.4898 MP. Solving this algebraic equation. Now R is equals to 0.5206. Check solution is plastic hinge at A. Now you get that R is equals to 1.4 P minus 0.167 MP. At C you get that 2R is equals to 3 MP. Therefore, P is equals to 1.18677 MP. Now you substitute R and MP in this question. You get that R is equals to 1.5 MP. Now check solution with plus and B and C. You get that R is equals to 1.5 MP and P is equals to 2.2624 MP. The true plastic collapse PC is equals to minimum of 3 calculated P values. PC is equals to 0.4898 MP, corresponds to the mechanism with plastic B. Now substitute values of P and R corresponding to the mechanism with plastic hinge at A and B back into the general bending moment diagram for the structure to determine whether the yield condition is satisfied. Now, Bm at A is equals to MP, Bm at B is equals to MP, and Bm at C is equals to 2R. Now you get that Bm at C is equals to 1.0412 MP, which is less than 3 MP. The plastic moment of the frame C lies on. It can be seen that the yield condition is not violated anywhere on the frame. Therefore, this provides confirmation that the assumed mechanism with plastic hinge at A and B is actual collapse mechanism. So thanks for watching this video. I'll see you in my next video.